then let us go ahead and shift gears a little bit, because we want to start talking about another aspect of modeling. And that is going to be the whole aspect of just really starting to think about the mechanical systems in the air and how things are moving around in the building. And how we approach that whole issue, because it's really pretty interesting and amazingly complex about like how all the different systems have to work together. And let us talk about how that stuff actually plays out. So I'm just going to put robot aside. I'm going to go back over to Revit. And I'm going to suggest that, like I sort of started with a relatively simple structure in Revit, we actually start out with for the structure, we start out with sort of a very simple model just to get ourselves going and understand how to put something together for the mechanical purposes too. Okay, here's the basic principle. Let me see if we can sort of like kind of talk about the principle before we actually dig into the mechanics of the modeling. So here's the idea. In a building, as we're thinking about going through and having mechanical systems in the building, one of the first criteria you have to worry about is just fresh air, making sure air is moving and that we have a healthy amount of air. A certain amount of the air can be recycled, a certain amount of it has to be replaced all the time. And there's some very specific criteria for how you determine how that works. And let me kind of show you a little bit of guidance about how you figure that out. So there are some ventilation notes from one of my favorite texts that actually explains a lot of this stuff. And let's talk about sort of different ways of calculating air. Okay. Actually, I'll even start with the one that I showed last quarter, because I think it's actually interesting too. So if I say ventilation, let me just call it air changes. There are two criteria that you have to sort of worry about. One is the whole notion of just how much air overall has to move. Then the second one is how much fresh air has to be in the space. I'm going to go up to air changes as opposed to air changes per hour. I like that one better. For typical rooms and buildings. So this is the chart I showed last quarter, and I think it's pretty relevant what we're doing here. The total amount of air that has to move, as in number of times the air has to change in the space per hour, it's really kind of based on the occupancy and the density of people in the space and really what's going on in that space. So some things are actually relatively low in terms of the amount of air that you have to move in there. For a bank, for a typical office, for things like that, it's like, 3 changes per hour, 4 changes per hour. And let's just kind of think about what that means. If I went through and I had a space, I'll make it an easy space, 20 feet wide by 10 feet wide by 10 feet high, something like that. We say 20, 10, 10, so what is that? That's 2,000? Am I about right? I think that's it. Okay, so 2,000 cubic feet. Okay. So what this would tell us is if this was an office space, like a public office or a private office. Let's say it's a private office. Okay, I need 4 changes. Per hour. So what I got to do is go through and do the math to actually figure out just really how many feet do I have to move per minute. Okay, because that's the way a lot of things are rated. So I'll say 2,000 cubic feet. I'll say 4 changes per hour. Okay. Then I just have to go through and normalize, okay, by saying, okay, if it's cubic feet, changes per hour, I want cubic feet per minute. So what I have to do is go through and say, times 60 minutes. No, it's the other way. 4 changes, then per hour. Okay, because that is per hour. Basically, I need a 1 over 60 in here somewhere. I'm trying to think where it goes at the bottom. That's how I learned how to do it a long time ago. The factor label method. And then 1 hour for 60 minutes. Okay. Now I feel comfortable. Okay. So, Magic Maestro people. What's 8,000 divided by 60? It's like one of those tests. How about how good you are? Okay, if it's 860.
133.3.
What? 133?
133.3.
Excellent. 133. Okay, cubic feet per minute. Super. Okay, so in order to make that happen, a couple things have to happen. If we really want to change that amount of air in that space, we've got to have two things happening. We have to have some new air coming in at 133 cubic feet per minute. Okay. But we can't just kind of pump air into a space, because if we pump air into a space, very high pressure builds up and eventually the doors blow off or something like that. Or the doors actually get very hard to open. If you've ever been in a space where you can't open the doors, sometimes it's just because the air is imbalanced. You also want to pull away 133 cubic feet per minute. Okay. And if everything was super balanced, that would actually work out. That would be, it would never be high pressure, it'd never be low pressure. Air would hopefully flow through here. You'll notice as I place these things, I didn't put them right next to each other, because if I put the out right next to the in, what happens is I sort of get a lot of local mixing, but I don't really change the air. So that's not really very good. What I want to do is actually sort of put the in and the out kind of on opposite sides of the room. If I want air to move through the whole room. Okay? And as we go through and do that, we even go a little bit step further. In terms of your in and your out, very often what we'll do is we'll figure out, okay, where is it going to do the most good to go through and introduce the conditioned air, the air that's the temperature we want, versus taking away the air which is stale or has lost some of its power. Okay. And as we do that, here's how it often works. We will often go ahead and put the intake basically near the windows. Because what I would really like to have happen is, without that air, this air by the windows will tend to be very hot or cold. It's the one that's most affected by the outside conditions. So when I introduce the air, okay, which is at the right temperature, it kind of heats up that space. That's kind of cool. And the air slowly kind of flows through the space. And I try to pull it out on the other side. It really just does the most good to go through and do it that way. Okay, so next time you're hanging around in a house, check out where all the radiators are. Check out where all the registers are. They almost always are near the doors and windows and stuff like that. Because what we'll tend to do is, even in a big space, let's say you have a big building, is we'll use the strategy of out near the windows, we'll go ahead and introduce all the new air, or all the conditioned air. And then what we'll do is we'll sort of pull it back to the center. We'll have the outlets sort of be here. So what's happening then is we get this nice kind of flow through to the center and kind of take it out that way. So the supply will ultimately kind of feed kind of towards the center. I'm looking at a new plan there. So in general, that's one of the criteria. And this is just air changes. Now, if our life was so simple that it was only air changes, that'd be good. But it actually involves a little bit more than that. And we're going to complicate it just a little bit. Because if we were only concerned about air changes, we could do something like this. We could go through and take that air that's coming out, put some sort of an air handler in here, and then actually pump it back through over here. And what's an air handler? In a lot of ways, it's like a big fan. It's just something that's kind of pushing air. So it's got electricity coming into it, air's coming in one side, air's blowing out the other side. So it's just keeping air moving. And at some level, that would kind of work. But we're going to complicate your life ever so much in that what tends to happen is we can't just go ahead and kind of push the same air through, because what happens is the air, even though it's moving, gets stale. And you can only recycle it so many times before we sort of ultimately need to sort of start replacing some of that. We don't just want to resurface. So what we actually try to do is a little bit of this. We try to bring in a little bit of fresh air as we're going through, and we'll figure out what that percentage is. It might be 10%, it might be 5%. We bring in a little bit of fresh, and at the same time, we say, okay, I'm going to bring in some more fresh air. I can't pump all the air through. What I have to do is actually do a little bit of exhaust. And again, we want those things to be in balance. So ultimately, the same amounts moving through. So that's how we get fresh in, get out. And there's even these really kind of cool devices that sort of show up in here where somehow as the fresh air comes in, it gets heated up to the same temperature so that it's like this heat exchanging. You don't have to kind of, if the air is really cool out here, you sort of preheat it a little bit by just putting it next to the other air so that as it comes into the system, you don't have to heat it up so much. But that at a real high level is kind of a diagram of the type of system we're trying to devise. So let's stop there for then. How does that feel? Okay, moving air in, moving air out. It's sort of based on the number of air changes. Okay, but okay, let's think about that complication and how that goes. The complication looks like this. There are minimum ventilation rates in the breathing zone, okay, as opposed to, I guess, the non-breathing spaces, okay, where it tends to be based on this whole notion of the people. And you can say it's based on the cubic feet that are required per person, or you can sort of do it based on the area. We should probably calculate it both ways and sort of figure out what's going on. But it's all based on the notion that in different types of spaces, there might be different densities of occupants. Okay, and then based on that, just because we're all in here living and breathing and we need the fresh air, we need to go through and replace some of that. So let's take a look at those in terms of how things sort of work out. For example, cubic feet per person. Let's think about this. In a general conference or meeting room, it's about 5 cubic feet per person. In a cafeteria or a restaurant dining room, it's a little bit higher. Okay? In a science lab or an art classroom, it's even higher still. So, what do you think sort of drives that? Why would it be sort of higher in some applications than others? Like, in terms of just the amount of fresh air we're consuming. You have any sense about what's the difference between just kind of a general conference or meeting room or like being in a science lab or, it's interesting, even a computer lab, like this space has a higher rate. So what's different about those kinds of spaces relative to the breathing that's going on? Definitely it's the density of people. That's a piece of it. It's how tightly we're packed in here. There's also sort of a notion of, it's just kind of what the quality of the air is. Things like cafeterias and restaurants, more air needs to move just because there's fumes, there's odors, there's a lot of other stuff going on. Just sitting around breathing is not so bad, but restaurants, there's a certain amount of air that we'd like to kind of freshen up. By the time we start getting to science labs and art classrooms and other places, they're going to start having like fumes and off gases of different things that are going on as part of the process. That's a little bit higher. Lecture classroom, not so bad, 7.5. Computer lab, 10. Okay. Any idea about what's different in here relative to, if you're sitting in a lecture classroom, again, this is going to be cubic feet per minute per person. Okay. You're sitting there in your lecture classroom just listening to the lecture, and things are kind of okay. You're sitting in here in the computer lab. What's different about this scenario than being in the lecture classroom?
Computers.
Yeah. That computer sitting there in front of you is generating all sorts of heat, and it's kind of like adding to the load that we're sort of putting on the space. So we basically have to go through and kind of factor that in there too. So there's different ways of going through and looking at this. We can look at it from a people standpoint, we can look at it from an air standpoint, and ultimately it should sort of work out to be about the same answer. Let's see if we can figure out kind of the right sort of notion. So let's say this space was a computer lab, like the space we're in now. How would that actually work? So cubic feet per person is 10. Super. I'm counting around 3, 4, 5, 6, 7, 8, 9, 10, 11. About 11 of us, 12 of us in here. Okay. I could say that, great, so I need about 1,200 cubic feet per minute. Okay, based on the people in here. Just a lot more. That's interesting. Come back over here, though. The way we calculate it, though, is we get to sort of go through and sort of say there's some sort of occupant density per 1,000 square feet. We don't actually have to count the fact that we're physically in here. We're going to use sort of an overall average. So for a computer lab, it looks like the occupant density is about 25 per 1,000 square feet. How many square feet do I have here? Oh, I only have 2,000 or 200 here. Okay. So let's see if we can make the math for this work. I got my computer lab. It's hanging around at about like 25 people per 1,000 square feet. Okay. So that's the sort of density. Okay. Now we have to multiply it by how many square feet we actually have in the space. So times 200 square feet. Okay. I can tell using my magic math mind that somehow it's going to be about 5 people. So if I say 5 people, and I come back over here in terms of cubic feet per minute per person, I'll come back over here, that's 10. Times 10 cubic feet per minute per person. So I think I'm going to get basically 50 CFM. Does that make sense? Yeah, catch me on my math. I'm often bad on doing math. You know, I can try for that. Okay, so, what does that tell us? Yeah, over here you told me that I needed 133 cubic feet per minute. This is telling me that I need 50 cubic feet per minute. Okay. So this is fresh air. This is air. Okay, so what I need to have going through here is I got 133 coming in here. I need to make sure that basically 50 of it are coming in. Okay. I need to have 133 going this way, or more. So I have to basically make sure that 50 are being exhausted. And I got to do a little bit of mixing in there to make sure that I always have that right balance between in and out. So really what I have to do is have to take that 133 and I'm going to subdivide it. I'm going to say, great, for that 133, I'm going to go ahead and take 50 and scoop it off the top. I'm going to take the other, 70, 83, and send it through. And then add the 50 back in. And that's the basic design of a system. And that's not too off the bad. So, and then 50 is coming through like that. Sort of make sense? Excellent. Okay. If that makes sense, let's take a look at it in terms of what a typical system looks like, and we'll start modeling it. So here's what we do. We come on down. Oh, there's all sorts of stuff in here. Just for our application, ours are a little bit different. In terms of our buildings, if we're sort of an assembly space, you could say we're like a museum or a gallery. The ratio is just a little bit different. It's not quite as bad as a computer classroom, but there's definitely some ratio that applies to our space, and that's really what dictates the amount of fresh air we're going to have to be adding into the system. So once you have that total amount of fresh air, again, just more and more in here. Evidently, disco dance floors and health club aerobics rooms, you're going to need a lot of fresh air in there. And I can imagine that. They get kind of steamy. Yes?
Just a quick question.
Yes.
So if you have operable windows, how will that affect the air handling?
Yes, you can bring in fresh air through the operable windows. And it's one of these things, a well-designed system will take that into effect so that if the operable window is using natural ventilation, the mechanical ventilation is offset so that...
So you shut that 50 and assuming that 50 will come in?
Then you can pull it in through the windows as opposed to pulling in through the air handler. And then the system has to be pretty smart because there's certain times during the day when it may be hot outside, so we don't want to do that, but at night, the smart systems are whenever you can go ahead and use natural ventilation and pull that in instead of the artificial ventilation, yeah, we shift. Like, that's what this building does. If you've ever been in here late at night, and you're sitting in like one of the atriums, like the green atrium, and like 2 o'clock in the morning, like this incredible suction comes through that can pull the paper right off the wall. And what's happening is we're doing something called flushing the building, where up in the top of the atrium, like some vents have opened up there, and on the side walls, vents open up there, so that like just convectively, all the heat starts rising out of the building. And it really does. It'll pull the paper right off the table. It's kind of fun. So if you're here at 2:30, you get to enjoy that. Or get very annoyed by it because it gets very cold in the atrium all of a sudden, which is not so good. Okay, so here's the basic design of a building. This is just, again, from one of my favorite little mechanical textbooks. But it really is this whole notion of we have supply air and we have return air. It's going back to some central system, kind of taking care of these rooms. Okay, you have little air handlers, and ultimately we're going to learn that as we're bringing the air in addition to sort of just exhausting some of it and bringing in some outside air, we might need to condition the air. We're going to learn to add that in there, that really, okay, as the air is coming back in here, what we'd like it to be doing is, we're going to condition it. We're going to either heat it or cool it, depending upon what the temperature is relative to what we want the temperature to be in there. We'll add that piece in there, but it's really just another little piece. You'll have a chilling or a heating element that'll go ahead and can change the temperature of the air. Even in terms of what a mechanical room looks like, if you've never sort of hung around inside a mechanical room, it can look like, different ways. This is the top one is really the notion of we have a mechanical room where we have, there's a return air inlet. That's where the air is coming back from the space. Okay, we have some space in there, the cooling coil, and then we're ultimately going to send the air back out again. Okay? But what's happening here, there's a little bit of outside air intake that's coming down into the space through a shaft. So if we're someplace where we can't have the outside air coming in directly, we may have to bring it down to its own duct supply. This one's a little bit different. This is more an equipment room where the same basic functionality is happening over here, but we actually have a direct air inlet from the outside. So again, if you ever walk past the building and you go past that louver on the sidewall, there's all this air blowing out. That's what's going on. It's just the exhaust air or the intake air, and that's what's really happening. Let's try and put that together. Okay. In terms of these air handling rooms, the amount of room that's actually needed to go through and take care of just the air handling equipment, you can almost start sizing it up based on the size of the load. So this is just some real rough guidelines about how big room has to be. If we needed something that was going to supply this 133 cubic feet per minute, okay, down to the low end, the actual equipment would be somewhere around 5 by 3 by, could be up to 15 feet long. So we need a certain amount of space to accommodate that. And let's think about that, because even in terms of the space, there's a lot of places we can put an air handler. You don't just want them kind of hanging around any old place. Okay, so let's think about that for just a second. You have a hillside. You have your beautiful architectural wonder sitting on the hillside. That's doing whatever it's doing and being so interesting as a piece of architecture out there. Okay. When it comes time to go through and place that air handler, where can we put it? What are our choices? The roof is a great place for some buildings. Exactly. I could go ahead and put it up here on the roof. That's a very common thing to do. And if I put it up on the roof and I don't want everyone seeing my beautiful air handler, or maybe I do, because it's actually part of the systems that are controlling the building, you can decide whether you want it to be visible or not. So a lot of times on roofs, we'll put it there and we'll put some walls around it, leaving some airspace, but little parapet walls that are just hiding it. It's just visually screening it, because not everyone likes to look at air handlers. Although, if you get up on top of Y2E2, anyone been up on the roof? Excellent. So where are they? They're kind of in the middle. Okay, you can't see them from below because you have all that red tile sloping kind of hiding it all, but in the middle, They're all sitting up there. The roof is a great place. It's kind of out of the way. It exhausts very nice into the outside. It works pretty well. Okay. If you don't want to put it on the roof, where else can you put it? Any other suggestions?
I have a question about
Yes.
on the roof.
Yes.
Would it disrupt a green roof if an air handler was up there? Like, does it disrupt the air quality that's immediately around?
Immediately around it, so we would, yes, because it's sort of introducing a lot of hot air or sucking air all the time, either way. If we put it on the roof, we probably want to isolate it a little bit from the area that you're thinking of as your green roof. So, you might want to sort of put it behind some sort of screen or just off the beacon track a little bit. Because, right around it, all that air is going to, it'll be either too hot or too cold. Yeah, it won't be good for plants. So, you do want to separate it a little bit. Kind of baffle it out a little bit. Okay. If you can't put it on the roof, any other suggestions? Roofs are very common. Almost everyone puts them in the roof.
In the back of the building?
You could put it in the back of the building. You could put it in the back of the building. Oh, a very common thing is even in the basement over here, we say, great, I'm going to take this little space. I'm going to put my mechanical room over here. I'll take my air handling unit, put it right in there, and then I'll have all these little louvers on the back of the building that let me do the exhausting. And great, so I have my little mechanical space. But no, it's just fine. It kind of takes care of it just very, very well. So a second approach is to do that. You could go ahead and kind of put it out here, okay, which is probably not the most scenic thing in terms of what you're trying to do architecturally. Although, if at your home you have air conditioning, you're used to seeing these little condenser boxes, these little condenser coils kind of sitting around outside, often in the backyard near where your patio table is, kind of disrupting the view. And people do all sorts of things to hide them. Okay. A very important thing with these, though, is you like to have pretty clear air space all around it. So if you go through and because you're trying to hide it, you sort of put an incredible nice hedge all around it, it kind of blocks it from everything, you could really decrease its efficiency because it can't get the air flow through it that it's supposed to be getting to do what it needs to be doing. Okay. One other application that I just want to sort of let you kind of think about is on a hillside. You can often do this too. You could, even if you don't want to put it in the building, I could go ahead and basically put it underground over here. Okay, have it over there. I still need the ductwork kind of going up into the building, and then have some sort of a screen on the top of it. So that's another thing you see an awful lot. It's kind of almost like in a vault of some type. But again, the big thing is it needs exposure somehow to get out to the outside air. And you got to think about really what makes the most sense, just on your ground floor, on your roof, or even possibly external to your building. Okay. All of them are possibilities. Okay, so let's put our very basic system in place and see how we can do this. So, how about this? I'm going to go over to Revit. See if I can find it. And we'll just kind of create a very simple system to start with. What I'm going to do is I can go ahead and start with my architectural template, or I could start with the mechanical template. The only advantage starting with the mechanical template is it has a lot of good stuff loaded into it already in terms of duct sizes and all the air terminals and stuff like that. Not to worry, if you've already started in the architectural template, we can copy all those things out and kind of bring them into your architectural project. But just for today, let's go ahead and start with the mechanical template because it's all sort of geared up and ready to go. So I'm going to say new, mechanical, say OK, and it doesn't look too awfully bad. One thing though it does have set up that's kind of nice also though is it has different views which are optimized for the mechanical and the plumbing systems, so they're already kind of set up and ready to go. So it's not a bad one to start with. Okay, to get going, let's do this. I'm just going to sort of put a very simple building in here. Ever so simple. We are going to put some walls down. I'm not going to worry about the type right now, but it will ultimately matter because the thermal properties will help determine the loads. Pretty simple there. Let me just make those up to level 2. Okay, I'm going to go ahead and put a roof on this building. So in terms of that, I'll go up to level 2 and put some sort of roof on here. I'm not seeing that right now, and it's probably because the view range is set up so I can't see things. You know, let's do it on level 1 and go from there. By footprint. Pick some walls, I'll give it a little bit of overhang. Okay, I'm going to make it a flat roof right now just to make my life relatively simple. So I'm going to turn off all that defined slope. Do that. So here we are. Simple little building. Not very interesting, but it'll give us an opportunity to go through and put in what we need. Okay. We would like to go ahead and put this basic system together. I need to put in a little of air going away. I need to put a little air going in, and I also need to put some sort of air handler in here to kind of keep things moving. So let's almost start, not with the ductwork, but with just the notion of like these terminals and the air handler itself. So let's see if we can find some sort of interesting air handler out here. If I go to the families, it's under mechanical equipment. You can look for it that way. So we have some air handling units that are already loaded in there. Okay, we can sort of bring in one of those, or if you want to, you can go to the Systems tab, and I can say that I have some sort of air handling unit. It's under mechanical equipment. It just takes us to a separate section over there. So I can go ahead and just put in an air handler. Ultimately, we're going to learn about something called a VAV, which lets us go ahead and control the volume of the air. Okay, we'll need that too. But let's just kind of keep it simple now. I'm going to put a relatively small one in there. Okay, it's kind of hanging around over here. It's a vertical unit there. Actually, I actually want a horizontal one. Let me see if I can go out and find one of those. Mechanical equipment. We got all sorts of these things in here. Split system horizontal, split system vertical. I'm going to go for the horizontal one, just because as I think about it lying on the roof, I think about it more lying flat. Okay, I'm going to put it up at level 2. I could even put a couple feet above level 2, just to kind of keep it up. Let's take a look at that thing, just so we sort of understand it a little bit better. You can see it has both ins and outs in a number of dimensions. It has ins and outs in terms of the ductwork. It also has ins and outs in terms of like some piping. The piping is going to be for ultimately chilling or cooling or something like that. The big ductwork is, though, on one side, you see over there, it's got a big old intake. On the other side, it's got a big old out. Okay, it's also got a little electrical connection in here too. And ultimately, we'll wire all those things together. But we're doing pretty good. I got this thing hanging around on the roof. Next up, we're going to put some air terminals. Those are the things that are actually going to distribute air throughout the space. So in terms of those, here's how we can go ahead and do that. Air terminals are their own kind of class of object. We have supply terminals and return terminals. We're going to place them. It probably makes sense to place them, I actually put them in a ceiling plan view because they sort of end up on the ceiling of your space. So let's see if we can put something like that together. I'll go into my ceiling plan for level 1. Okay. I don't really have a ceiling. I could put one in there and kind of attach it to it. Maybe I should do that. Architecture, I'm going to say let's put a ceiling in there, and I'll put it, I could sketch it by picking some wall boundaries. Or I could auto it. Auto just makes it happen very, very quickly. Autoing it just sort of finds the boundaries for me. Let's see if I can get this right. So I'm going to put one there. It's interesting. It looks like I'm trying to draw. There we go. Finish that out. So now I am ready to put some air terminals in here. How about we'll keep it real simple right now. I'll put a couple of returns and a couple supplies on opposite ends of the building, and we'll go from there. Okay, so, if I want to put some air terminals in here, I will go to the Systems tab. Actually, I should pay attention to where my ceiling actually is. My ceiling's 8 feet off the floor. So what I'm going to do is on the air terminals, say that I'm going to put a couple supplies in there at 8 feet off the floor. And I'll put some supplies over on, let's say, this side and that side. going to go through and put the returns going the other way. So systems, air terminals, put some returns over in the other direction. Again, highly simplified. Oh, level 1 plus 8. I have one kind of sitting on the floor right now. I'll get rid of that in a second. Notice the difference in the symbols. The cross being the supply going out, the kind of single hatch being the return going back. Okay, so let's take a look at that in 3D just to kind of make sure we're looking pretty good. There's that terminal hanging around on the floor. That's not looking too good. We're okay in terms of what's going on. We are ready to start putting the system together. So in terms of putting together the system, it's all about just kind of putting ductwork together and connections and kind of make it all happen. And we sort of played around with this last quarter, although we're going to learn some new tricks for doing it a little bit more efficiently this time. What I can do is go ahead and put some ductwork in. Now, as you're putting in ducts, the same as not worrying about the size of the beams, because it will be sized for us, or we'll get some guidance about that. The ducts, you don't have to worry about it too often much, although it does help to get sort of close. Just because as you're planning things, you'll start developing an intuition about how big these things should be. So I'm going to actually change to a different kind of ductwork. I'm going to change to sort of a round duct. I can figure out whether I want to have a kind of big radius curves or short radius curves or just T's. I'm just going to leave them big radius curves right now. And for this, I can go through and choose the diameter of the duct, whether you think it's going to be 12 inches or 18 inches, whatever you think it might be. We also have some sort of level to put it on. So there's different ways of doing this. I'm just going to draw it in the ceiling plan. So ceiling plan, I'm going to put that piece of ductwork in there. Say level 1. I'm going to put it about 9 feet right now, maybe even 10 feet for that matter. Well, level 1, I think level 2 is that. Should raise level 2, so I have a little more room in here. So I'll put it at 9 feet right now. What I'm going to do is start by just drawing some ductwork. I'm going to get close to these guys. Draw some ductwork that goes across like that. Actually, I'm going to do a better job than that. That's not really the way it would work, more than likely. We would probably have a system that, comes on down from wherever the air handler is, and it would probably go off at like a 45-degree angle or something like that and get pretty close. To the extent that you can go ahead and have things come off at nice smooth bends as opposed to 90-degree bends, you tend to be better off. So what I will do is, though, I will get ever so close. I won't actually connect to it yet, because when I finally do connect to it, I tend to like to use a flex connection, which just gives a little bit of flexibility. You don't want too much flex duct, it's less efficient, but it gives you a little more just, variability in where that thing actually ends up. Putting hard ducting in is actually pretty hard to do. Okay, in the same sense, let me kind of come off of this one, and I could see if this will work. Tap in like that. Okay, and that actually, that did a pretty good job. Well, no it did. Y shapes and round ducts don't necessarily work too well together. I'll bring it out and come over there. Okay, but it's doing not such a bad job on that side. Let's take a look at that in 3D. You'll see I got this kind of round ducting system. It's looking not too awfully bad. What I'm going to do is actually do a little bit of connecting. What I want to do is just really start to create a system out of this whole thing. So what can we do? I can go through and choose that guy, and I can say connect it into, and then choose up. In this case, it's not going to do it, because what's happening is just given the geometry and the amount of bending that has to happen, it just can't kind of complete it, so I won't do it that way. I'll put a piece of flexi duct in there instead, and just go from the connection there. Did I get flexi? It's funny, it's not showing it to me. I actually sort of swear that it probably is there, because I put the end cap on there. Did it do it? It's not showing it to me. Let me go ahead and raise this whole system. Nope. I'm going to leave it at that for now. Hang on. So I can close it on the other side. Again, FlexiDuct will go from here to there. Okay, that one it did okay. I might have to pull that one back a little bit in order to kind of give it the space to do what it needs. Let's see if I can get the FlexiDuct going this way now. From here to here. Okay, that's not looking too bad. So I got one side of the system. We're kind of building it okay. What I need to do ultimately, though, is connect the system in, okay, to the air handler so it all is working together. As you look at your system over there, this is a supply duct. That's a supply terminal. This actually isn't tied into a system yet. We're going to tie it into a system. Showing up as supplier, that's okay. What I need to do now is basically go ahead and tie it into the out on the air handler. So I can go ahead and keep on extending it. I can take this over a little bit further and ultimately go through and connect that into it. Let me see if I can do it this way. I can say connect into, this might work for me. Let me go for the supply air side and connect it into that. No, it's going to have a little trouble with that, so I'll route it myself manually. Oh, you know what it is? Because I have this, I cursed myself for putting this 18-inch duct in there. We are going to connect those things together and do it for both sides. And a couple things we'll do next time that'll actually hopefully make it make a little more sense in terms of like playing around with the sizing here. We are going to connect them together on the supply side. We're going to connect them together on the return side. And when we have a complete system, we'll see how it can actually help us compute the total amount of space going through there and what the cubic feet per minute is to help us actually size these things so that ultimately it'll help us figure out how many of these terminals we need as well as really what size all these ducts should be. Because the ducts are actually determined by the amount of air flowing through and criteria about like how big they need to be to maintain the right pressure and not have static buildup in them.
Oh yeah,
It's very smart about that. So we will continue that next time with the model and actually hold together a little bit better, but the basic principle is just like this. Okay, let us break for tonight.